the waves are either constructive or destructive. Okay? She paid a lot of money for destructive interference. Yes. Oh, come on! You got a gift like that? God. In any event, those noise-canceling headphones create destructive interference. You can, if I've got wave and a wave that looks like this, and then I got another wave coming back this way, looks like this, then what happens is when I start adding up the tops and the bottoms, I end up with something that's stupid like this, right? And we call that destructive interference when it happens. Now, when two waves stack, it becomes what? Constructive, or makes the thing louder. Yes, sir?
Is that what hearing aids do? They do the opposite.
No, hearing aids typically is taking a sound and then amplify it next to your inside of your ear.
You should show me.
Is it called amplifier because it increases the amplitude?
Yes, exactly. That's exactly why it is. Now, movie theaters are designed intentionally for destructive interference. Why? Because you don't want sound coming from the wall, coming from the speakers, reflecting off that wall, and what happening?
You hear it like
You don't want to hear it at all. So they basically, those walls don't reflect anything. I shouldn't say destructive interference. They have no interference at all because they're killing all the sound. If you go to a good opera house, one of those places that they actually set up the stage, and you go to the stage, and by the way, our stage does just a smidge. It's not great, but it's just a little bit. With a little bit of design, I can make a noise, we whisper on stage, and you can hear it in the stands. How is that? Because all of the reflected waves bounce off the walls and then go out in space, right? And if you make everything bouncy, then you can have constructive interference with yourself. And so people around the room can actually hear the sound better. There is a ticket you can buy when you go to Milan. There's an opera house there. It's a great opera house. It was designed by somebody famous, and I forgot who, to make constructive interference. It is such a perfect balance in the room that you can stand anywhere on stage and whisper, and people can hear it anywhere in the audience. It's amazing. Except for 8 seats. You can buy those 8 seats. In those 8 seats, guess what you're going to hear?
nothing.
Not a sound. Because that's where the waves cross each other and make constructive interference. You have to lean left or right to hear stuff. You actually, the tickets are cheaper if you buy them. Isn't that cool? So a good physicist will go to the summit just to sit in a bad seat. They're actually marked differently because they don't want somebody to accidentally sit in them. Okay? But because of the way that the walls are set up, at that very spot, you're going to hear nothing unless you lean left or right.
How do you measure that?
We can measure sound waves. How loud a sound wave is with a meter. So back then, it was just the old-fashioned. Why is this person? This person starts. Person actually is laughing their heads off, and you're like, wow. Where did I go recently? I went to some college recently. With BYU. BYU. Is that BYU? Walking around BYU, they have a central courtyard. They have all these little alcoves set up. And if you go into the alcove, anybody whispering can hear everybody else in the alcove. You step one step outside, it's gone. Because all the walls are designed to amplify that noise. But the moment, because of the way it's set up, it all focuses in the center, it goes back out, it diffuses almost immediately outside those alcoves. So you have a private conversation with 100 people in the same little alcove, step outside, nobody can hear you. Somebody walks in, you say, we're talking about you. Weird. I'd never seen anything like that. I'm walking around and my daughter showed it to me and I'm like, this is the greatest thing ever. She's like, now we have to go someplace else. Yeah. All right. All right, I'm going to pause here. I'm going to make you do a couple problems for me, and then maybe we'll get some of the rest of this stuff done. I got to pause indicated. So the first one, how far will the waves have traveled? 10 meters per second, 0.5 seconds. They'll have traveled how far, Walker? 10 meters per second and 0.5 seconds. How far would they travel?
He's traveling 5 meters.
He's traveling just 5 meters. So I would look at this and go, this wave over here on the left is going to look like it's going to be starting at 9, it's going to go up to 1, and then it's going to spike back down at 6. Is that right? This wave over here will have moved 5, so that puts it at 16. So this wave is sitting right here, being very bored, not doing anything interesting. Got it so far? Great? Okay. Draw the next one if you haven't already.
Why are these shaped like
You can make waves that are really blocky looking. It's possible. They're doing it so it's easier to see what's going on because when it's curved, it's hard to tell where exactly am I adding or subtracting. It's really easy when you have blocks to figure out what the diagram is supposed to look like when you're done. Another 5 seconds later. So that's at 9, so it'd be at 14. So this wave would look like this. Great. Oh, I'm in the wrong spot. I'm in the wrong one. Great. And then this one here would be where? 11. So it would be like this. And then that spikes downwards. Would it be 1, 2, 3, 4, 5, 14? That would. So it goes down like this as well. So what do these waves look like? What does it look like when they're maximally interfered with each other? Constructive interference. It's constructive or destructive, first of all? The amplitude is going to be 2 in the middle, right here. This amplitude is going to be 2. Great. Everybody see that? 0 plus 1, this is just going to be 1. In between, I'm going to have 1.5, so that's 1.5. And then I'm back down to 0 over here, aren't I? So this wave's going to look like this when you get done. I'm just adding the amplitudes. Okay, which way does this new wave go?
Going left.
And go
Yeah.
like that.
Those are the areas.
It's a trick question. They keep going, right? They re-separate back into where they're going. So this wave is going to end up over here. Oops. A little too tall. I'm sorry, everybody. And this wave is going to end up over here. Going that way. That make sense? All right. So as part of your homework, you do number 2 later. You're also going to do 10.5, which you're going to pass out now. And then we'll have brownish wave sitting here, the grayish wave. Now, when they interfere with each other, they're going to have both destructive and constructive because they don't have the same frequency, right? It's actually rare to have the same frequency. That's why we talk about reflections when we talk about the same frequency. So because of that, here we're going to have nothing, right? When they line up, we're going to end up with nothing. When they line up the other way, though, we're going to have what? Constructive interference, which is going to make a big spike. And then after a while, they're going to get out of phase again, and eventually we're going to end up back where they're opposite again. We have nothing. In between, the waves are going to slowly get bigger and bigger and bigger till the maximum, then slower and slower and slower and slower. And then, if you have 2 frequency devices, you not only hear this, but you also hear this kind of strange getting louder and quieter. That's what amplitude is, louder and quieter. We call this wave, this distance across from here to here, we call that a beat. Okay? The beat frequency is when you have both constructive and destructive interference because the frequencies are not the same. You have both constructive and destructive interference, which leads to these strange pulses, right? The actual frequency of the combined wave looks like this, right? But you'd hear this kind of overtone of louder, louder, quieter going on in the background. Again, I'll try to get out the team doing first next time. Who knows what will happen tomorrow morning or Tuesday morning, but I'll have the next time for listening to. Okay? Does that make sense, sort of? And how would I calculate such a thing? It's actually the easiest calculation of the whole stupid test. You look at it. Yeah. I'm going to make you draw a couple of these. You're not going to think that's the easy way a little bit. I take the derivative. I don't even know what that means. Come on. How many times is it going to change from minimum to maximum?
2 T's.
If I have a frequency of 240 hertz, and I have another one that's at 241 hertz, how many times is the second wave going to pass the first wave? Once. So how do you calculate the beat frequency? Subtract the two frequencies. That tells you how often you're going to hear a beat. Right? Because that's how many times the first wave is going to pass the second wave.
What's the beat sound like?
Measure things. It just sounds like it's a little bit louder and a little bit quieter. That you can hear the two sounds together. They make kind of a weird noise together, and then on top of that, you're going to hear it kind of get louder and louder and louder and louder. Yes.
So the beat is like that wave outline.
It's like this. It's like the wave outline. Yeah. It's like if you drew the amplitude wave. It's actually the frequency of the amplitude waves.
Actually, one beat would just be over the
Yes.
top.
Look at this.
Oh.
Right. 1 beat. Right. So it goes from where they completely cancel out to where they completely cancel out.
Is there such thing as a beat frequency?
That's what we said. The beat frequency would be how often that would happen, right? So you might hear that.
Beat frequency, or is it just called beat?
It's called beat frequency. And the thing is, the beat frequency, the thing about the beat frequency is this, is it sounds like a different sound to you. Because you can hear this in addition to the other two waves. So you actually hear the beat frequency. It's louder, it's quieter, it makes a different note to you. It sounds like a different pitch. Okay, and back in good old days when they used to know how to write music, they would intentionally make beat frequencies so you could hear all the different musical instruments playing, but some of them were creating an intentional beat in the background that would be in addition to that. Now, if we want to make a beat, we have a guy in the back with a drum, and he goes, bam, this is the beat right here. I hit the drum, and that's how you know where the beat is. Back then, they used to try to make it, they would make the beat throughout the thing. They'd change the instruments, but the beat would stay the same. But it was in the background. That's how they tried to make the beat happen. Now, again, we have a much simpler system. Just hit the drum really loud.